Hello all of you. Welcome to the 30th lecture on the course on analysis and modeling in chemical engineering. In this week, we have been discussing about heat equations. We started with the general derivation of the heat equation starting from energy balance in a microscopic control volume. And then we discussed the case when we had a one-dimensional version of the heat equation for heat conduction in a slab, and how can we get analytical solution for simple cases when we have homogeneous boundary condition, and how to frame the problem in more complicated cases when we have non-homogeneous boundary condition. So, today I will apply it on a case study on somewhat of a real world problem, where we are looking at the formation or making of biscuit in an oven. So, the idea here is that, of course, you may have all had biscuits in your life, and you must know that the biscuits are made typically in a oven. And the basic recipe of making a biscuit goes something like this. So, we mix flour with butter and water and we make a dough that is wet, and then we put in a oven or a microwave. That's what I am showing here. And what is the beauty of the microwave is there is a controlled heating from all sides, compared to, let's say, if I put on a tawa. I took an example of roti in the last class, where the heating was from only one side and other side was exposed to ambient. In this case, the heating happens from all the side, and that uniformly makes the biscuit. And what happens as a result of heating is the moisture inside the dough or the water inside the dough that evaporates, the butter melts, and they basically form like bubbles that evaporate, which gives you the crispy nature of the biscuit. And you wait long enough, and then you have certain level of crispiness in the biscuit. And if you wait further long, you can have what is known as caramelization, where a caramel kind of a thing forms. That's the reason why we'll prefer to have an oven or a microwave, because we can go to higher temperature in a controlled environment. And then finally, you have a biscuit that you can take it out and cool down, right? So, I want to use the idea of heat equation that we have discussed, along with the moisture transport inside the biscuit, to frame a mathematical problem that can give you some kind of a process model for biscuit making. So, the problem statement goes like this. So, the process of, I am outlining the process of making biscuit in an oven that contains typically the following steps, and you may be aware of these steps. The first step is the oven is preheated to a temperature that is something like Ta, that is higher than the evaporation temperature of water, let us say Tv, at the pressure condition inside the oven. That is the best first requirement, because you want to evaporate water. So, it is, you can say it is some kind of an evaporator, but with a solid biscuit surrounding it, right. So, we must have temperatures higher than the boiling point of water at the given temperature, given pressure, and we prefer to preheat it, because I can directly put the biscuit inside while the temperature is going up, but then the model becomes somewhat of problematic, because the temperature, ambient temperature, also become time dependent, and that is also not practically good for the biscuit making anyway, right. So, we preheat it to a certain temperature that is already there, and now we make a dough outside of a certain shape, consisting of the flour, the sugar, butter, whatever you prefer, and the other ingredients, and then place inside the oven, and the oven doors are then closed, so that we have a closed heating environment inside the oven. And now, as a result of heating, what first happens is the butter melts and the dough becomes slightly hot, and then there are multiple enzymatic processes that begin inside the biscuit, right. So, what I want to highlight is, apart from just the heat transfer and evaporation, you also have few chemical reactions taking place when that happens. And then, as the temperature of the dough surface exceeds Tv, it will take some time for the dough to reach a temperature of the boiling point of water. In that condition, the evaporation of the dough moisture begins, and as a result, what really happens when the temperature of the dough surface exceeds something like a Tm, that is a much higher temperature, then in that condition there are chemical reactions which also happen, so called the Maillard and caramelization reactions. They help in two ways. One is that it can give you biscuits which are like sans moisture, so it can be stored for a long time. And second, at the surface you have some browning that gives you a nice taste of the biscuit. You don't want it to overdo it, that the biscuit becomes black, but you want to have some surface browning effect. And this gives you a characteristic texture and taste of the biscuit that you are interested in. And finally, the biscuit is taken out. Once the biscuit has very little moisture left, I mean pretty much no moisture, but probably that is difficult to have, and we have achieved the desired surface texture, right. So, based on this recipe, a simplified process model for the biscuit making based on this description can be developed in the following way. We can assume that the starting duff is a cylindrical shape and has a uniform temperature T naught to begin with, and the air temperature inside the oven is fixed at TA because we have preheated and then we maintain that temperature. And as what I said in the very beginning, the whole reason why we need microwave or an oven is to provide uniform heating from all sides. So, we assume that the duff experiences similar heating from all the sides. And we also assume that the duff dimensions do not change with time. If you want to be like very accurate, you can imagine that the duff may shrink because of heating or may expand depending on the material inside the duff, but we are ignoring those effects because anyway those effects are assumed to be small on the biscuit behavior. So, if we make these assumptions, then the temporal and spatial variations, because the temperature inside the duff is going to depend on time and also depend on the location inside the biscuit that is being formed, that can be given by the heat equation. There is a small catch here that the moisture evaporates inside the biscuit, and therefore, there is a heat source inside the biscuit, but we are going to assume that all that bubbles that form, they immediately leave the biscuit, right, or the duff. So, therefore, it does not provide an additional heat source inside the biscuit, but we take care of that in the boundary conditions at the surfaces, as you can see here. So, what we say is there are two conditions here. One, the temperature of the duff is less than the vaporization temperature or the boiling point of water, and at that condition, at the surface of the biscuit, we have the usual condition that we have defined for the slab, that is the conductive flux from inside the the biscuit or the duff, it matches the convection flux going out. And in a general notation, the conductive flux is given as something like this, where n is the normal direction for the surface of the biscuit, and we can define it also on the sides, but we will assume later that I will ignore the sides because of the one dimensional approximation. But in general, it can also be basically there are multiple normals, one normal from the top surface and another normal from the sides, and also normal at the bottom surface, right. So, this condition kind of takes care of all the surfaces of the biscuit, and that is equal to the convective flux when the temperature is less than vaporization temperature or the boiling point of water in that condition. And once that temperature exceeds the boiling point, in that case, in addition to the convective flux, we also have the additional heat which is coming from the vapor, and that additional heat is function of the heat of the vaporization multiplied with the density and the mass transfer flux, the diffusive flux at which the moisture is coming out, and the diffusive flux is given as something like by the Fick's first law as d into the gradient multiplied by the normal at the surface, and that is what is written there in the general form, and we will simplify it for one dimensional case. So, here again rho is the density of the duff, Cp is the specific heat of the duff, We will assume that the rho is constant, but in reality the rho is also changing, but for simplicity we can assume that the density of Duff is constant. The heat capacity, the specific heat, is also assumed to be constant, and T is the temperature of the Duff, that is now a function of the spatial location and the time, and small t is the time elapsed since the Duff is placed in the oven. K is the thermal conductivity of the Duff, again assumed to be constant. N cap is the outward normal vector, as I have demonstrated just now. H is the heat transfer coefficient, and delta H vaporization, delta H vap is the enthalpy of evaporation of water, and then D is the diffusion coefficient of water through the Duff. Keep in mind that diffusion coefficient of water outside will be much higher, but since it is passing through the Duff, therefore there are obstacles on its way of water molecule diffusion. So, this will be some sort of an effective diffusivity of the moisture inside the Duff, right. Now, if you think about it, the water mass transport, the moisture transport, if it is in the form of bubbles and all that, it can have contributions from diffusion and also convection. But just to simplify and to get a starting point of a model, I am going to assume in the simplified model that we only have diffusion phenomena from which the moisture is coming out, right. So, provided that the amount of water inside the Duff is not very high, this is not a bad assumption, because what the diffusive flux will be the one that will be the most dominant in those cases. Okay. And then we also define water content of the Duff as the amount of water in the Duff divided by the amount of Duff, and this varies with the spatial location and time, and given by this equation in general, that is the Fick's law, subject to the boundary condition at the surface. Just like for the temperature, the boundary conditions look like this, right. So, we had two conditions, one for the temperature less than Tv and one for the temperature higher than equal to Tv. Similarly, for the moisture also we have two conditions, one for temperature less than Tv, right, and that is the diffusive flux at the surface is assumed to be 0, right, because for T less than Tv no moisture is evaporating, so it cannot escape, right. Only when we exceed Tv the moisture starts to evaporate, and once it starts to evaporate, just like the heat transfer coefficient for the case of temperature, now we have in place of H we have the mass transfer coefficient Kc, and instead of the temperature difference now we have the difference in the water content in the ambient and inside the Duff. So, XWA is the water content in the air assumed to be constant, and Kc is the mass transfer coefficient, and then the initial water content of the Duff is assumed to be uniform and equal to some XW0. So, what we are asked is to draw a schematic diagram of this system and write a suitable one dimensional version of equations and the corresponding initial and boundary conditions. And after that, we have to make a suitable choice of dimensionless variable, just like what we did for the heat equation. We want to do it in this case and write the equations with their boundary and initial conditions in dimensionless form, such that all the variables except time vary in the range of 0 to 1. And then we are asked to identify the two time scales in this system. There is heat equation and we are also doing diffusion equation, right. So, you can imagine that there are two time scale intuitively, but we will see like what it comes out to be, and we are asked what are their physical significance. So, let us begin with this. So, we assume that we have a cylindrical Duff, and just the typical shape of a biscuit is such that the radius is much bigger than the length, right. The overall length or thickness is something like 2L. So, provided that R is much bigger than 2L and therefore, R is much bigger than L, we can pretty much ignore the R direction gradient. We can consider gradient only in the z direction, just like what we did for the slab case, right? So we can assume that dou t by dou z is much higher than dou t by dou r, and same we can do also for the moisture, that dou xw by dou z is much bigger than dou xw by dou r, and therefore we consider equation only in the z direction. And then because we have uniform heating from all side, we can again assume that we have symmetry in the theta direction. So in principle, as we have said, in cylindrical coordinates, you will have derivative with respect to r, z and theta. But since we are assuming symmetry in theta direction, we are ignoring the theta variations, right? So we are not considering that term. And now we have a one-dimensional equation in z direction, and further I can draw a symmetry plane at z equal to 0 and consider only the upper half of the biscuit. That's pretty much amounts to assuming that t at z, provided that the center line is z equal to 0, is equal to t of minus z, which has to be the case because this point at z from the center line and corresponding point at minus z, they are pretty much getting the same heating environment. They are as far from the surface, right? Both are equally far from the surface, right? So the heating is same. So we can assume Tz is minus Tz, T of minus Z, and therefore we can solve only in the solution domain, which is above this center line symmetry, right? That is upper half of the biscuit. So now we can write the equations, and in this case we have two equations, one for the heat transfer and other for the mass transfer, which in this case I have assumed it is a diffusive mass transfer of the moisture that is going out. Nothing else is going out. We can assume that all the other component of the duff is pretty much non-volatile. So, they are not going out, only the water is going out. And as I said, the vaporization gives you extra heat, and we are assuming that all of that goes away immediately with the vapor, just to make things simpler, right. So, now we are doing it half the domain, and we have basically two variables to solve for: temperature as a function of Z and T, and the moisture content as a function of Z and T, and we are solving in the domain going from Z equal to 0 to Z equal to L. Now, we can worry about now the initial conditions. So, we assume, as I said in the problem, that at time t equal to 0, the temperature is uniformly T naught, and at time t equal to 0, the moisture content is something like xw0 to begin with. We can look at now the boundary conditions for the temperature. So, at center line, we can assume no flux that comes from the symmetry consideration. The same thing that we did for the slab, we are also doing here. And at the boundary, we are essentially simplifying whatever equation was given in the problem for the case of one dimensional heat equation, right. So, we can go back and look at the equation given in the problem. So, now del T, in reality the del T is going to be something like Ex Er dou T by dou R plus E theta dou T by dou theta by R plus Ez dou T by dou Z, but we are ignoring the first two terms and we are left with only this, and the n cap vector for the top surface is simply Ez. So, basically del T dot n is going to be something like simply dou T by dou Z, because we know that Ez dot Ez is equal to 1. So, this term gives me dou T by dou Z, right. The same idea we can apply here. So, this becomes something like dou xw by dou Z at Z equal to L. Okay. So, now we have these boundary conditions, and we have two boundary conditions, one for T less than Tv and other for T higher than equal to Tv at Z equal to L, the top surface. and z equal to 0, we have the center line condition, the symmetry condition. The same thing we can do for the moisture content. We can basically look at whatever boundary condition we had and then simplify it for the one dimensional case. So, again we have something like this. Again, from the same logic, at the top we can write del x w as something like E r dou x w by dou r plus E theta by r dou x w by dou theta plus E z dou x w by dou z. We can drop the first two terms for the reasons we have stated, and the n cap vector at the top surface is simply E z, and therefore I can write del x w dot n at the surface as something like dou x w by dou z at z equal to L, which is exactly what I have written here, right? And the left hand side, right hand side is as we had, and again we have two conditions for t less than Tv and t higher than equal to Tv, and at the center line again we have the symmetry condition, but now for the moisture content. So, now these are the final form of the one dimensional model which we have derived. So, we have essentially two partial differential equations to solve for, one for the temperature, one for the moisture content. This is my first boundary condition at z equal to 0, that comes from symmetry. The flux is equal to 0 both for temperature and moisture content. And then the second boundary condition at the top surface is different for t less than Tv and t higher than equal to Tv, and we have one boundary condition for the temperature and other boundary condition for the moisture content, and we do have initial conditions for both the equations, right. So, there are two PDEs, and for both of them I am specifying the initial condition and two boundary conditions, and therefore, they are kind of independent at first glance, but keep in mind that there is a coupling between the two, and the coupling is coming from the presence of this term dou x w by dou z in the boundary condition of the temperature dou T by dou Z, right. So, I cannot really solve the temperature equation without solving simultaneously the moisture content equation, because the boundary conditions are coupled with each other, right, and this coupling is what makes the problem more difficult. If, for example, the evaporation was not happening, then in that case we simply have, let us say if I look at only the first equation here and first equation here, then there was no coupling. So, I can solve for the PDE for temperature separately and the PDE for XW separately, but now since for T higher than equal to TV we have this coupling. First of all, it makes it somewhat non-homogeneous, but more importantly we cannot solve them independent of each other. We have to solve both the PDEs together, right. Okay. So, now we can define the dimensionless variables in the spirit of whatever we have done for the one dimensional slab, right. So, T cap is defined something like this, and you see at time t equal to 0 we have T cap is equal to T minus T naught, because temperature is T naught at time t equal to 0 for the Duff, by T a minus T naught. So, this becomes equal to 1. So, we start from 1, and for T going to infinity, eventually the temperature of the biscuit will become the temperature of the ambient, provided that we wait long enough. We do not want to wait so long, because then we get a pretty much a black biscuit, but provided that we wait, then we are going to have something like T cap is equal to T a minus T a by T a minus T on is equal to 0. So, T cap perfectly varies in the range of 1 to 0, which was the idea, the expectation in the problem. And the same thing I can now also do for a dimensionless moisture content. If you think about it, the moisture content was already dimensionless earlier as well, because moisture content was defined as the amount of moisture by the amount of Duff, right. It was dimensionless, but it was not varying in the range of, let us say, 1 to 0. right? In fact, it will vary from some number to begin with, because in the beginning the initial moisture content is some fraction and then it goes to 0. So, just to make it consistent with the dimensionless variable of temperature, we can define a dimensionless xw in the following way. And now you can see, just like what we did for the temperature at time t equal to 0, my xw is going to be xwa minus the moisture content at t equal to 0 is xw0 by the same quantity, which is equal to 1. Just like the T cap is 1, the xw cap is also 1. And if I wait long enough, then eventually whatever moisture content we have should be the moisture content in the oven. And we are assuming that the oven is much bigger space than the small biscuit. So, the ambient moisture content is unaffected pretty much by the whatever moisture it gains from the biscuit, right, because the ambient may already have some moisture, and ambient is much bigger space anyway. So, the moisture of the biscuit, once it evaporates, it does not make much difference in the ambient moisture content. So, in that case we are going to have xwa, and xw eventually, if I wait long enough, is going to be xwa, and this also goes to 0. So, again, just like T cap, xw cap is also going from 1 to 0. Z cap I can define as Z by L, but the T cap, now you can see and remember like how we defined time scale in when we did the heat equation. So, we defined the time scale starting from here, whatever made the time dimensionless, we used it in there, right. So, once we made it dimensionless with respect to temperature, I had something like T cap here, T cap here. When we made Z dimensionless, we had Z cap here and K by L square coming here. So, once this thing went on this side, basically we got a time scale rho Cp L square by K, which was the time scale I used in the heat equation of a slab. But now we have two different PDE. So, I can apply this idea on both the PDEs, right. So, if I apply the same idea on the other PDE, once I replace xw with xw cap by the same argument, this will not change the PDE pretty much. But when I change z with z cap, I am going to have d by L square z cap square, and now I have got another definition of time scale, that is something like L square by d. And now the question is, which time scale do I choose? I can choose any of them in reality, but we have to be very clear which time scale I want to prefer, right. So, let us say I use the heat equation time scale. So, that means tau h is equal to as I had earlier, but keep in mind that we have a tau d there. And now, if I use, for example, this definition of T cap in the second PDE, you already have a L square by d appearing there. So, now you imagine I will have something like dou x w by dou T cap, will have a tau h coming here, and then we have something like 1 over tau d dou 2 x w by dou z square. So, we have therefore a factor tau d by tau h appearing there, and therefore, the PDE, the second PDE is appropriately modified. We have an extra factor chi, because we have not used the tau d as the time scale, we have used tau h as the time scale, right. So, now similarly the boundary conditions also gets modified in terms of the dimensionless variable, and the same is true for the second boundary condition. I got the Biot number similar to what I had there, but now you can imagine that since we have something like a delta H web rho d there. So, if I make it dimensionless, I will get some other dimensionless variable. I am not giving the expression for that, but you can figure that out. So, I am defining one dimensional variable eta here, and the same thing for the moisture boundary condition. I will get another dimensionless variable, let me call it SH. In fact, it is called the Sherwood number, but that is besides the point, right. And then we have the initial condition in dimensional form like this, but I can write in dimensionless form as T cap Z cap 0 is equal to 1 and X W cap Z cap 0 is equal to 1. This is the final form of the equations that we have got, right? Now let us look at one last problem, that is assuming that the browning of duff begins. I told you in the very beginning that if I wait long enough, then we start to have this Maillard and caramelization reaction. So let us assume that the browning of duff begins when the duff surface is heated beyond a certain temperature Tm. That can be represented by a chemical reaction of the form A to B following first order kinetics, let us say, where the concentration of A is proportional to the sugar content at the surface of the biscuit, right. So, we are assuming that this is the sugar that is basically getting burnt kind of and giving rise to that browning effect, right. Now, how can we incorporate that effect in the equations derived in B, and how is that expected to influence the temporal and spatial variation of temperature? Just think about it, the reaction that I am getting from here, it can be endothermic or exothermic, and whatever heat of reaction I am getting is now the extra heat that I have, right. So, just like whatever I had here, let us say here in this case I accounted for the evaporation until here, right. So, now I will add another condition for T higher than Tm, right. So, this is for T higher than equal to Tv and less than let us say Tm, and for T higher than equal to Tm I will add one extra term in whatever we have here that has something like the heat of reaction that we are having and multiplied by whatever conversion or the rate that I have in there, right. So, whatever I did for the energy balance of the reactors, right, that will give me something like an extra term coming here that will account for the browning process, right. How does it affect? It depends again as whether the reaction is exothermic or endothermic. If we assume that it is endothermic, let us say, then some of the heat that is coming out by evaporation, that heat is now available for the reaction, right. If it is exothermic, then it is other way around. We are getting basically heat from evaporation and also heat from the reaction, right, and accordingly the temperature profiles will get affected because of that, right. So, this is how we can basically apply the heat equation on real world problem. And since I have said that heat equation is pretty much analogous to the diffusion equation that we have in the mass transport, in fact also equal to a momentum transport equation, analogous to a momentum transport equation, right. So, the same kind of an idea can be applied for a variety of problems in transport, right. So, I have taken an example of the biscuit making, but you can think about other real world context when we have this partial differential equations and all that. Until so far, I have only discussed an analytical method of solving this partial differential equation, that is variable separable method. And as I have discussed, the method is quite limited in scope because it can only do it when the boundary conditions are homogeneous. So, we need to have mechanisms to solve it numerically, which is one of the methods is like called the finite difference method. And in the next week, we will also discuss the finite difference method when we talk about the numerical methods of solving equations. So, with that I conclude here. Thank you so much.